Hey there folks, today we're going to talk about groundwater. So groundwater, as you're hopefully guessing, is water that is stored in the ground compared to surface water, which is water stored obviously at the surface in lakes and streams. You may be wondering what it's stored in underground, and hopefully as throughout the course of this lecture you'll understand that a little better. But the gist of it is that it's stored in what we call pore space, in rock or sediment. Believe it or not, when you looked at these sedimentary rocks, there was tiny little spaces, pores, in between the grains, where the cement was that held various grains together. You also have some space or area where the cement isn't, and that's called pore space. And the water can trickle into there very slowly, as you can imagine, and it moves through there. Not quite as slowly as you'd imagine. So we'll go through all of that as we explore this a little further. Just to put this in perspective, here's a water cycle, which we talked about. Once the water falls to the surface of the earth, it can do one of two things. It stays at the surface as runoff, streams and lakes, as I mentioned. And then we also have the idea that it could percolate into the ground and become what we call groundwater. All right, so we're dealing with the groundwater component of that right now, the trickling. So we're going to do a little zoom close up here of the ground. We've got some precipitation happening, a little tree there. And we're going to ignore a couple words right off the bat here. I want you to ignore this vadose zone. We're going to use a different term. And I want you to ignore the word capillary fringe there. We'll probably acknowledge both of those words, but don't pay them much mind right now. More so, I want to focus your attention over here to these two squares. These are enlargements. These are enlargements of the pore space in this brown area and the pore space in this blue area. Okay? And you see how the pore space in the blue area, there is all blue, whereas up here, you see that there's some white in between. The white, they could have pointed to a bigger space here, but the white is air, or what we're just going to call gases, okay? And the blue is water. So what we have basically is an area deeper down that is called the saturated zone. And what we're referring to with saturated are the pore spaces. They are completely 100% full of water. They're saturated, all right? Whereas up here, what we're going to call the unsaturated zone, or the zone that is not saturated, you see that your pore spaces are not saturated with water. You still have some air present. All right, so that's the big difference between the unsaturated and the saturated zone, is the presence of air or gases in the unsaturated zone. That's what this vadose zone was referring to, was sort of the unsaturated zone. If we could just put the word un in front of this, there's no need to learn another vocabulary word at this point, okay? And plenty of people use the word unsaturated zone. So, like I said, ignore this vadose here. We have the saturated and the unsaturated zone. And again, the difference is in the saturated zone, you only see water. And in the unsaturated zone, you've got water and gases. All right? Now, separating those two, my mouse keeps disappearing. I don't know if you guys can see it dancing all over the place, or even when I can't. Sorry if I'm moving it way too much. I want you to look at this blue line here. All right, this blue line represents something called the water table, and this is an actual area. It's a plane. Remember, this is not just a two-dimensional diagram, but in reality, it's 3D. Okay, so this blue line would go into the computer screen, into the, a distance, and it marks a surface. Basically, it is the top of the saturated zone. It is the last area where the pore space is completely full of water. This becomes important when it comes around to, say, drilling a well, okay, whether it be personal or even at the community level. If a community makes do on groundwater, all right, it's in your best interest to make sure that your well is drilled well, pardon the use of the word there, well below the water table. Let me ask you guys, and some of you know this, some of you may not. Is the water table fixed? In other words, is it constant, or can it move up or down? Well, it can move up or down. If you're in a period where there's a whole lot of precipitation or snow melt, okay, you're going to have a lot more water trickling down into the ground, and that could fill it up to higher levels than ever before. Your water table rises. If, however, you're in a period, a drought, okay, of very little precipitation, it's been months since there's been snow melt, so on and so forth, that water table can certainly drop as it gets used up, all right? And not even necessarily right here at this little well. It could be used up downslope, it could be used up upslope. These are usually very, very large regional sort of things that we're talking about here. So it's not just these folks in their nice little crank well that we've got. So the water table can vary, okay? And the water table marks the boundary between the saturated and the unsaturated zone. The last word that's on here, again, I said, don't pay it too much mind, is capillary fringe. Capillary fringe simply tells us that some water will move a little bit above the water table. Call it paper towel effect, if you would. You know how if you just set paper towel just barely touching a puddle or whatever, the water will absorb into it and move through the paper towel. It's the same idea, but it doesn't really enhance our knowledge at this point. So, okay. And this is just sort of a recap of the vocabulary words we talked about: the saturated zone, the unsaturated zone, and the water table. All right, two more terms for you: porosity and permeability. And I've used the word pore space several times, and that's what this word porosity is about. It's counting how much pore space there is in whatever area you're looking at, okay? It's a measure, which is in a percentage, of pore space in a body of rock or sediment. And in order to think about this, I usually use a sponge. Picture maybe you have one sitting on your kitchen sink to scrub your dishes with. All right, and think of that rectangular little sponge there. What percentage of it is holes, and what percentage of it is spongy material? I'm just going to pick some random number here, and let's say that it is 60% spongy material and 40% holes. In other words, 40% of the total volume of that sponge is empty space. 60% of the total volume of that sponge is the actual spongin material. All right, so if 40% of it is holes, then we would say it has a porosity of 40%. Okay? If, on the other hand, you decided it was 60% holes, you would say that it has a porosity of 60%. Now, our other term here, permeability. Permeability is a measure of the interconnectedness, giant word, I had to convince spell check it was real there, of the pore spaces in a body of rock or sediment. Interconnectedness of these pore spaces. In other words, we measure how easily the water can flow through. You see this lovely word I've made up here, flow through ability. All right, permeability is a measure of flow through ability. How well can the water get from pore space to pore space to pore space to pore space? Sometimes those pore spaces are connected, and sometimes they're not. And it's not always the case. I mean, you might assume that if something has a low porosity, that, okay, there's only a few holes in this rock, and there's a good likelihood that they're not connected. You're right. Okay, but the opposite isn't always true. Even things with a high porosity, they might not be connected. They might not be connected. I do not want you to memorize anything in this table here. Okay, we'll give you some nice generalizations, but this is here just to give you an idea of what's going on. All right. Generally speaking, loose sediment is much more porous and much more permeable than solid rock is. Goes to figure, of course. It's not compacted a whole lot. It's not glued together. There's not cement in the way. Okay, so that makes perfect sense. With rocks, some are better than others. In the context of this lecture, which, by the way, groundwater can be an entire 14-week class. I know you've heard me say that a couple times already. You could spend a whole semester in a class about groundwater, so we're just barely scratching the surface here. But generally speaking, and throughout this lecture, when I talk about rocks holding water, usually we're talking about sedimentary rocks, okay? Because of the way they're formed, igneous rocks, the crystals grow together one by one, very, very close to one another. Igneous rocks don't have hardly any pore space in them. A few obvious exceptions, pumice, okay? And if you do hear somebody talk about getting groundwater from an igneous rock, and granite aquifers are highly prized, don't get me wrong, that water is sitting in giant cracks that are in the igneous rock itself, just like a giant vein, okay? Not going through the pore spaces, but sitting just in a giant opening, okay? So when we talk about pore spaces and water getting through, just picture sedimentary. Now, that being said, all these qualifiers, shale, mudstone, absolutely horrible, okay? Shale loves to suck up water, so you might see a fairly decent porosity on it. You see shale here can go up to 30%, okay? But it hates giving up its water. In a little bit, when we're going to be talking about some scenarios here, I'm going to refer to shale as like Tupperware, okay? It will not let anything pass through it. It'll suck up all the water it can, and then it becomes impermeable. It may as well be, as I said, a layer of Tupperware holding everything in. So I don't want to get ahead of myself, but generally speaking, if I were to ask you just a point-blank question on the test, what kind of rocks make the best aquifers? We haven't used that word yet, but that's an aquifer is a body of rock or sediment that yields water. You would say sedimentary rocks. Okay? Okay. Hey, there's that word. Aquifer. All right, an aquifer is a body of rock or sediment that yields water. You might see in the textbook where they write significant quantities of water. All right, I'll show you in a minute why I don't think we need to say the significant quantities, because if you're going to say, well, it's right here. If you're going to say that it's an aquifer, that should imply that you've got plenty of pore spaces for water, and that it's fairly easy to get that water out. And that's what the permeability means, is how easily you can get that water out, how well it flows through those pore spaces. So in here, an aquifer means a body of rock or sediment that holds a good amount of water and that you can easily get out. Okay? Okay. Because they're going to tell you about two other kinds of aquifers, and I put it in quotes here, that by definition they really aren't that good. We have aquitard on this page and aquaclude on this page. All right, aquitard, aquaclude. So an aquitard, think about what does to retard mean? Retard means slow. So an aquitard is a layer of rock or sediment that yields water very slowly. That is probably due to low permeability. The unsaid implication is that there's water there, it's just hard to get it out. It's a pain in the butt. Okay, if you had to, yeah, you could use it, but if you got other choices, don't use it. Aquaclude, as in exclude, okay, that gives up no water, or it has no water. All right, there's two choices here. Typically, we use it to refer to that shale, as we were talking about a couple minutes ago. Very low permeability. There's probably some pore space there. Okay, it can hold some water, but you aren't getting it out. But it also, as I say, possibly low porosity. Okay. Also, potentially, you could talk about one of those igneous rocks as an aquaclude. So, what it boils down to is that in a lot of the parts of our country, at any rate, you've got so much sedimentary rock at the surface, okay, that these groundwater studies just typically involve sedimentary rock. Now, as I said, there are parts of the country where you do have igneous rock, granite aquifers. New Hampshire, Vermont, okay, over in the northeast area, over that a ways, and I'm sure there's other parts of the country. But for the majority, the Midwest, the East, okay, where we are, I don't know too much about further out west, but I'm pretty sure it's mostly sedimentary out there. Groundwater studies focus around sedimentary rocks. So when we say aquaclude, again, you're pretty safe thinking shale. So you follow this here. Aquifer has plenty of space for water and it's easy to get out. Aquitard probably has plenty of space for water, but it comes out very slowly. And an aquaclude, either it doesn't come out at all, or it just doesn't even have any space for water. So I want to shy away from calling this 3 types of aquifers because, as I indicated, I really don't think aquitard and aquaclude are aquifers, because by definition, an aquifer, good porosity, good permeability. Anyhow, I don't want to beat a dead horse here, but the other reason I don't want you to think of those as 3 types of aquifers is because now I'm going to tell you that there are 2 types of aquifers, 2 scenarios in which we've got water stored in rocks. One of them called a confined aquifer, and another one called an unconfined aquifer. And we'll have some diagrams here in a minute, but basically what we're going to talk about is whether or not there's a lid on these things, okay? We're going to talk about the aquifer itself, which will be the rock that can hold water. Then we're going to talk about an impermeable layer, okay? In both cases, we're going to have a bottom to the aquifer. It'll probably be shale or something similar, all right? The difference is whether or not it has a top layer. The confined aquifer has a top and a bottom. It has a lid on it, as I said. The unconfined aquifer is just open to the surface, if you would. It's like having an open trash can that can collect rainwater, or a trash can with a lid on it that's not going to let water get in. All right. As we said here, there are implications to this. The confined aquifer is harder to fill back up. The unconfined aquifer, as I implied, the open trash can scenario there is very easy for water to trickle down in. You'll see it a little better with the diagrams. All right, so we got a couple things going on here. This slide was originally about something called a perched water table, but let's first understand that this is what we're going to use for our diagram of an unconfined aquifer. All right, unconfined aquifer. Now, depending on the class that you're taking, you may or may not know what these little dots represent with regard to rock type. Okay, in geology, we talk about rock symbols. In earth science, we don't necessarily cover that. So in either case, I'll let you know, this refers to sandstone. Okay, sandstone is considered a fairly porous and a fairly permeable rock. Down here underneath, we can't see it, but down here underneath, we have to assume at some point there's a layer of something that's going to be impermeable. I suggested we always use shale, okay? Shale is that Tupperware bottom. It's going to absorb some water, and then it's going to become impermeable, all right? And from that point on, lost my mouse again, from that point on, the water is going to start filling up. Now we see that water table again showing up here from our first diagram. All right. The important thing to notice here, because this is an unconfined aquifer, is that for the most part, please ignore these bits of shale here. For the most part, there's no lid. The water can trickle right down into here, filling up this aquifer as easily as you'd like to. Let's move real quick to this one just to show what I'm trying to explain here. Then we'll get back to these other vocabulary words. In this diagram, however, where we see the confined aquifer, here's our shale. Shale is dashed lines. Here's our dots, so this is sandstone again. And you see they've got another layer of shale on top. All right, it's a sandstone sandwich here, or a shale sandwich. Shale's your bread there, sandstone's in the middle. The water is going to hit this and flow right downhill once it's absorbed as much as it'll hold. So this impermeable layer on top here leaves the only area that you can fill this up at right here where this sandstone is exposed to the surface, which is quite different than here where almost anywhere here the water will trickle down in. So this is what we meant by limited recharge with a confined aquifer, all right? But much easier to recharge here. So confined aquifer, again, has a lid and a bottom, has a top and a bottom that are both impermeable. An unconfined aquifer only has a bottom, and you can't see it in this diagram, I apologize, but okay, so you understand the difference between a confined and an unconfined aquifer? I hope so. So what are we talking about here? Perched water table. Well, this means perched as in up high above. And what we just told you is that the dashed lines mean shale. We also just told you that shale will absorb some water and then it'll become impermeable, right? Which means it'll stop water from flowing through it. So what they're implying here, you'll also see the word perched, you'll see the word false sometimes in parentheses next to it. You'll see perched or false water table, or you'll see false water table or perched. They vary on what word they put in parentheses. If you don't know what you're doing, okay, you're trying to save yourself a couple $1,000 and you're going to borrow a giant well drilling drill, you go to Taylor Rental and get one instead of hiring somebody. Okay, it's hard to tell scale on here, but let's just say this is a good bit of drilling you've done already. So you go out in your backyard and you start drilling your well, and you're like, man, I went 100 feet without any water, and I've been, good 50, 75 feet with water in it. We're in the there's not sputtering out or anything like that. We must be in the aquifer. And you quit drilling. You hook up your pump, hook up your house to it, and lo and behold, you hit a dry season, and this water's going to disappear because you're still a good couple 100 feet above the real water table. Okay, that's one of the problems with a perched water table. Generally speaking, well logs are public record. I made a silly scenario there. You wouldn't be drilling your own well, but you might hire, like the Japos do, hire the cheapest contractor you could find, right? you might get somebody inexperienced who doesn't necessarily know what they're doing. Please, find out what your neighbors, how deep their wells are. Okay, if everyone else's well is at 400 feet, make sure yours is at least 400 feet. Okay, keep an eye on these people, because not everyone knows what they're doing. A perched water table can also do something rather cool. All right, and you don't have to have a perched water table to get a spring, but in this example, a perched water table is giving us a spring. A spring, which we'll have a slide in a couple minutes here, its own slide, is when the water table intersects with the topography, intersects with the land. Okay, it's when the water table leaks out at the surface. When we talk about streams in class, we'll tell you that in geology we only use one word for streams. Okay, not river, not creek, not crick, not brook. We just call them all a stream because we need to keep it simple. There's one exception to that rule, and that is a spring. Okay, and a spring implies that the source is groundwater leaking out. So you go and you buy this fancy bottled water that says spring water. Well, they better dang well be pulling that right out of the leaky ground. Okay, or it ain't spring water. So, so in this case, the perched water table gives us a spring. Now, if you've spent any time driving the thruway in the wintertime, you've noticed this phenomena quite a bit, because it also gives us those amazing ice flows on the road cuts. You seen those? So white they're almost blue. Okay, this layers of shale there, and what happens is the water trickles down. It hits that, and it flows. Just the way the rocks are sloped there, they slope towards the highway. So you get in springtime, you get these nice little waterfalls every so often, but in the wintertime, those ice flows are so cool, and I've been meaning to take pictures of them for way too long now, and I haven't, but hopefully you've seen them and you know what I'm talking about. Look like frozen waterfalls coming out of the side of the rock. That's basically this idea here. So perched water table is a false or a fake water table. It's well above the main water table. It can cause trouble if you're inexperienced in drilling a well. Okay, and it can also contribute to an occasional spring flowing at the surface. All right.